What's up, AS Math? It's Mr. Knight here, and we are going to start this little mini unit on vectors. They're going to come in handy because, well, we've already kind of worked with vectors, and we're going to continue to work with vectors going into next semester. So once again, you could see that we have a force diagram. It is whatever object we made, whatever it is. It's a box, has some mass, and it has some kind of force that's pulling it in one direction, okay? The force is a vector. It has a direction associated with it. A scalar is just some kind of value that doesn't have any direction. So mass is a good example, okay? We've seen something like this, but what if I have something that looks like this now? Let's say I have some kind of other like force, some kind of maybe rope around this, and it's pulling up at some kind of direction. I'll call that force B. And force B is still a vector. It still has a direction, but now it's not just a matter of left to right. It's got some kind of, well, it's got some kind of angle to it now, right? But nonetheless, they're all vectors. Now, both of them have some kind of direction, and both of them have some kind of magnitude. Magnitude is just a fancy way of saying size or length. It's just kind of how long something is or how big something is, okay? With vectors, there's just a lot of terminology that we got to establish first before we start working with them. So for example, you could see something like this. I took this force B, I kind of rotated it around, and now it's kind of going in just this direction. So what we could do is we could say, all right, FB, let's say it equals 5, then its magnitude, its size, is going to be 5. Its direction, however, we can just say is 30 degrees. And we are saying positive 30 degrees. So counterclockwise is always going to be positive. But if I said negative 30 degrees, well then I would be down here having some kind of angle. Negative 30 degrees would be going the other way. Okay, so this is always going to be positive. Counterclockwise is positive. And we'll keep that in mind as we move forward. Now, when it comes to working with vectors, there's kind of two different ways of writing them down and expressing them. And here is the first one. The first one comes down to, well, the magnitude and direction of what we were just talking about, those two components. So we call this magnitude direction form. Wonder why, right? Magnitude direction, and then we also call it polar form, so you might see it two different ways. R is just our magnitude, theta is our direction, and so we can express that as 5, 30 degrees. No big deal, right? The other one is called component form, and it's a little bit different. And by a little different, you're like, that looks way different, okay? It is kind of way different. So we have some kind of vector A, and we could say that vector A, and when we say vector A, you either will see it like bolded like that, or you'll see it kind of with an arrow above it. And so vector A equals 4i plus 2j, okay? We'll talk about that in a little bit. So when we break this down into components, you can think about some kind of line having a rise and a run, okay? It has some change in y and some change in x. Well, this I and j, we call those unit vectors, which we'll talk about later on in the next lesson more. But unit vectors basically are just vectors that have a magnitude of 1, and we just assume that that's their size. But really, they're more important to just tell us the direction, okay? This is way more important. This is more of like the actual definition, I guess, if we're going like closer towards that. But if you want to just tell me, hey, it's 4 units in the x direction and it's 2 units in the y direction, this is how you can express that, okay? So I and j, and so we can represent that as 4i plus 2j. If we were going the other way, like let's say it was negative 4i, well, negative 4i would be coming the other way. So you could maybe have something like, if I have something like this, that would be negative 4i and then this could be like a positive 2. Okay? Or if I had something that's going down here, again, you could have -4 going in that direction, but now you could also say -2 for my j. So to express that, I could write that as the a vector is equal to, we do our x direction first, -4i minus 2j, and that's how you could express that. Okay? There's a lot of different ways to express vectors. They also represent it with 4, 2, like that. So if you see it like that, they just mean 4 in the x direction, 2 in the j direction. I would definitely write all that down, even though it seems like, wow, we're all over the place. Let's just kind of see how these problems are going to boil down. Okay. Like I said, vectors are typically in bold, or with a line above 2 points. So if I had like this guy right here, I could write 0 and p. So the vector from 0 to p could be represented as the vector from 0 to p. Something like that. Anyway, let's see some examples. Let's see what's going on. So a lot of your homework today is going to be looking at those 2 forms that we just talked about, and either changing component form to polar form, or going the other way, polar form to the coordinate form, or the component form. So for this example, we're going to take it in component form and write it in polar form. So we have some kind of vector here, and really it's that same vector we just used for that example. So let's see kind of how to work with that. So for magnitude, if I want to find the size of this guy, well, this kind of looks like a right triangle. If I wanted to find the hypotenuse, how could I do that with this right triangle? Well, I could use Pythagorean's theorem, right? And that's all you got to do to actually find the magnitude of any vector. You just need to take all the sides, square them, and take the square root of it, and you will get, apparently for this one, 4.47 for a magnitude. Now for the direction, that's actually this angle right here. There's a little bit of trig, but it's more about plugging and chugging, okay? So to find theta, to find this angle, we need to take the arctangent, and this should be of j and I. The arctangent. Okay, let's see that in action. So the arctangent, if we look in our calculators, our TI-84s, the arctangent is going to be the secondary function. So the secondary function of this guy right here, of tangent. It's kind of hard to see. And so I can do something like that. I get the arctangent. And all I'm going to do is I'm going to do my j over my I. Whatever my j number was over my I number. Well, in this case, I was going up 2, and I was running 4. Yeah, so I'm going to go ahead. I'm going to plug this guy in. Arctangent 2 over 4. And I should get 26.6 degrees. And I go to turn it in, and what the heck? I got 0.46. What happened? Well, if you did this too, you might have gotten a different answer, just like I did. And maybe some of you got this one. The reason is our mode needs to be in degrees. Okay? So make sure on your calculator it's degrees. Let's try that again. Arctangent of 2 over 4. And look at that. We end up getting about 26.6 degrees. Okay? So make sure your calculators, the mode is switched to degree mode. And there we go. We'll be able to get our direction. And so I could say that the vector A is 4.47, 26.6 degrees. That's exactly how we expressed it here when we were looking at our 2 forms. Okay? Magnitude can also be written as this. This is kind of the absolute value symbol. And so if I wanted to say the magnitude of A, I could say it equals 4.47. Okay? A lot of different ways to express these. A lot. Okay? So now I want you guys to try this one. I want you to try and write this vector in magnitude direction form and just see how far you get. Okay? Go for it. Got it. All right, we're back. All right, let's see how to do this, guys. So we have this 4j, -5i, and we have this direction right here. Now, this direction right here is really only associated with these guys right here, just like this part. And really, this is the true direction that we're trying to find. Because before, we only went, about like 30 degrees. Now we're going past 90 degrees, okay? Well, if I know what this angle is, and I subtract it from 180 degrees, that'll give me whatever is left over right here. So that's what I got to end up doing, okay? So again, the magnitude, that has not changed. I'm still just going to do Pythagorean's theorem. I'm going to end up getting 6.4. For my direction, however, it's a little bit more involved. Once again, I know to take the arctangent, don't worry about this part, worry about this part. I know to take the arctangent of my j over my I, so that's going to be my 4 over 5. It's in degree mode, hopefully now. So I end up getting 30.87. And that's my theta. So to get my alpha, my true direction, I need to do 180 minus this guy. I end up getting 141.3 degrees. And so my vector in polar form is that guy right there. Okay, not too bad. All right, let's see going the other way. Let's take something that's in polar form and let's put it in component form. So here's my r, and here is my theta. And let's kind of see and go through how that works out exactly. Well, we don't really have a whole lot of tools yet, but here's a good general rule for this. Okay, so this is magnitude direction to component form. All right, so we could write r comma theta like this, but more importantly, we can write it like this. Okay, where it's r cosine theta I plus r sine theta j. So really, guys, to get it back into component form, the only thing we got to do is take whatever our magnitude is and then multiply it by cosine sine of whatever angle, whatever our direction is, and just slap on the I and j. That's all we got to do. So if I take this guy, here's the magnitude, 10, here's my angle, theta, and there we go. I'm going to put 10 cosine 290 in my calculator. Again, make sure it's in degrees. And we end up getting 3.42i. And I put plus minus, but you could just put minus 9.40j. And that's it. Just use this general rule to go from magnitude direction to component form. Okay? If it makes it a little bit clearer to you, maybe write the component form part on your notes, so you know what you're doing with that thing. Okay? You can also write it like this, the magnitude direction form. You can compute it to make it look more like that. And that really comes from, looking for it in my notes, really comes from this guy right here, where it could also be represented. So that's another way to look at it, okay? Oh yeah, we already went over that, Mr. Note. So you try, write 5, 60 degrees in component form. Go ahead and do that and give it a shot and go. All right, we're back. Let's see what you came up with. So here is our vector, magnitude 5, 60 degrees. Again, we just take our magnitude, and then the cosine is for our I, the sine is for our j, and then we take that stuff, and then there we go. We are done. So you should get this guy right here. Now, there's a little bit of miscellaneous information with vectors that I think we should just touch on for a second. For example, there are 3D vectors. Okay, we've been working with 2 dimensions. You're not really going to work with 3D too much in this lesson, but I want you aware of it because they will pop up. Really, the key difference is we have this I, j, and now k. The k is for the z direction, okay? So I can write point P as 3i, 4j plus k. I could write it like that if I wanted to, if I was representing a 3D vector, okay? A couple other things. Magnitude. Magnitude for 3D vectors. This goes along with that. It's written the same exact way, found the same way. It's kind of weird to think Pythagorean theorem, I guess, but you're really just adding up your x, y, and z components and squaring them, taking the square root, just like you would do with 2 dimensions, okay? Equal vectors. When they say that these vectors are equal, that means not only is their direction the same, but their magnitude has to be the same as well. They have to literally be going in the same direction. So you have to have something that looks more like that. And even that, based off my crappy drawing, they are technically not in the same direction, so those aren't even equal. But let's pretend they are going in the same direction, right? Same size too. Now, position vectors. This is the last thing, I promise. It's a vector that just starts at the origin. So if I have, my origin right here, and then I have vector OA, my position vector of A is this OA right here, okay? I'm just assuming it's starting here. That's different from vector AB, which is something from, well, point A to point B, okay? It's not my position vector. It's not the position vector of A. Position vector is literally only starting at the origin, and that is the only difference, okay? This is Mr. Knight, signing off. Good luck on your homework.